Okay, hello. So there's an analysis of variance and we want to compare the means. We are going to start with the hypothesis, followed by the degrees of freedom. Then we are also going to look at the degrees of freedom from the degrees of freedom hypothesis, degrees of freedom. Then we also look at the sum of squares, then the mean of squares. After looking at the mean of squares for our data, we are going to move on to also look at the F statistics. We are going to calculate the F statistics. Then we are going to use a table to find our P value. Then we interpret our results, whether it's significant or not significant. So now here we have three groups: compact cars, mid-size cars, and full-size cars. And with that, we are going to look at the individual values. For group 1, we have x1, x2, x3. So we have 3 observations for group 1. Then group 2, we have also 3 observations, making x4, x5, x6. Then group 3, we also have 3 observations. So they are all 3 for each group, x5. So that will be x7, x8, x9. So in all, we have 9 observations for our ANOVA data, analysis of variance data. And we know that as a whole population, we have 3 samples. So on the average, we have average for one average for compact cars, second average for mid-size cars, and third average for full-size cars, forming our whole population, which is termed as the population mean or the grand mean. So we are going to begin with our calculations by first stating our hypothesis. So in stating our hypothesis, which is our first steps, this hypothesis is a tentative claim that informs our study. So we start with the null hypothesis. With our null hypothesis, we believe that whatever it is that we are going to test doesn't exist. So here we say that the null hypothesis, there is no significant difference between the means of the group. There is no significant difference between the means of the group. With the null hypothesis, there is no significant difference between the means, or we can say that since we are dealing with the pressure of cars, there is no significant difference between the mean pressure of each car. So statistically, we're going to say that mean population 1 or population mean 1 is the same as population mean 2, and it's also the same as population mean 3. Then with our alternative hypothesis, that one is the opposite of the null hypothesis. The alternative hypothesis is the opposite of the null hypothesis. So here we state that there is a significant difference between at least one of the means of the group, right? Yeah, at least one. Because it's likely we'll have 3 different possible outcomes for the alternative hypothesis. So with the alternative hypothesis, there is a significant difference between at least one of the means of the group. Here we can say statistically, we can say that the population mean 1 is not the same as the population mean 2, and it's not the same as population mean 3. Or we can say that the population mean 1 is the same as the population mean 2, but it's not the same as the population mean 3. And the list goes on and on and on. So that's it for step 1, with stating of hypothesis. Now step 2, let's move on to our degrees of freedom. Here we are going to look at how the between groups deviates, how the within groups deviate and how the whole group, that's a total group, deviates from the main population. How each samples deviate from the main population. So now, degrees of freedom between the groups. With the degrees of freedom between the group 1, group 2, group 3, we have K. K stands for groups. K stands for groups, where K minus 1 will be the group. The number of groups is 3. Will be 3 minus 1. So K minus 1, which is the group deviated from 1, will be 3 minus 1 will be equal to 2. Then we have the degrees of freedom within the groups. That's the number of observations that we see minus 1. The number of observations that we see, minus the group. So N, which is our number of observation, minus K, which is the group. So we'll have N is 9. We can see 9 observation minus the group 3. So 9 minus 3 is 1. Then our total will be N minus 1. That's the total number of observation, 9 minus 1. Note that the between groups plus the within group will give us the total number of groups. So 2 plus 6 will give us 8. 2 plus 6 will give us 8. So that's it with the degrees of freedom. Now we are moving on with we are moving on with the sum of squares. Sum of squares. With sum of squares, we are going to sum the squared deviation for within groups, between groups, and the total number of groups. So in order to keep our work organized, we are going to put it in a table. Pardon my rough table. I wasn't having a ruler. Pardon my rough table. So we are going to create a table so that we arrange each of our values under a section. Ideally, the question, you will find the table being structured there, so you can copy the table and rewrite it on your questionnaire. So in our data source, we have the between groups, we have the within groups, and then we have the total groups. Now that we have our table organized, we can see our table, right? So we can go ahead and record the degree of freedom between, degree of freedom within, and degrees of freedom total onto our table. So we can see it over there. 2, 6, and 8. Now let's move on to calculate our sum of squares. Remember that the sum of squares has to do with squaring the deviation of how each mean deviates from the grand mean, or how the mean individual observation deviates from their individual means. So it's squaring the deviations and summing everything up. Let's begin with sum of squares between. So with sum of squares between, this is the formula. We have the summation of each group, each number of group. Then we have the n, summation of n, which is our observation. Then the mean minus the grand mean. The mean minus the grand mean square. So we have our sum. We have the number of observations that we see there. We also have the mean for each group. We are going to fish out the mean for each group, write it down. Thus, we are working for sum of squares between. So between group, we subtract the mean from each group. We do the mean from each group minus the grand mean. Mean for each group, group 1, group 2, group 3, minus the grand mean. So we have the number of observations. We have the mean for each group. Now we need to look for the grand mean. Right? Because we don't have the grand mean. So how do we calculate our grand mean? We need to find the grand mean before we can go ahead and calculate for the sum of squares between. I repeat, we need to calculate our grand mean before we go ahead to calculate the sum of squares between. So let's look at our grand mean. With our grand mean, we have mean 1 plus mean 2 plus mean 3, all divided by the number of means. The number of means here is 1, 2, 3. Okay, so that one will give us our grand mean. 1, 2, 3. When we add all, it will give us our grand mean. So let's go ahead and put the values in them. Let's go ahead and put the values in them. So that's what we get. When we add the values, we get our grand mean, which is 529.22. 529.22. So now we have our grand mean. Let's go ahead and calculate our sum of squares between. Sum of squares between. So for sum of squares between, we have the mean for group 1, which is 66.67, minus the grand mean, which is 529.22. Then when we finish, we put them into brackets, right? They're into brackets, square. Yeah, so you organize them well. Times the number of groups. The number of observations, times the number of observations. So we have 3, which is the number of observations. In group 1, we have 3 observations. Yeah, times the mean of that group minus the grand mean, all squared. Then we do for the next one, the number of observations for group 2, then the mean of that group 2 minus the grand mean, all squared. Then we do for group 3, the number of observations for group 3, then the mean for group 3 minus the grand mean, all squared. So when we finish, we compute it using our calculator, right? We compute it in order to find the sum of squares between. So we take our calculator, then we do the calculations. We enter all our calculations. So we have, we can see that we have for each one, we use our calculator. We have for group 1, we enter 666.67. You do it one after the other. So you first work the deviations. You work the one in the bracket, then you square it before you come and multiply it by 3. You work the one in the bracket, you square it before you come and multiply them by 3, right? So you first work on the brackets, then you square each of them. After you get your answer for each, you pick each of the calculated squared value, then you multiply them by the number of observation. So which is 3 times the first squared value, then 3 times the second squared value, then 3 times the third squared value. Then you get your sum of squares between, which is 86,052. 86,052. Then you come and record it in your table. You come and record it nicely in your table so that everything will be well organized. 86,052.83. So that's it for sum of squares between. Now let's move on to look at sum of squares within. Now, with the sum of squares within, there are two ways of calculating for this deviation. There are 2 ways of calculation for this deviation. First, we can use the individual observations minus their mean, the group means. We can use summation of the individual observation minus the group mean square. Or we can use the variance approach, which is summation of each individual variance times the degrees of freedom. Now the mistake I realized that we're making in classes, with the degrees of freedom, we are multiplying it with the variance of each group. So whenever you finish, we need to divide it. We need to split the variances among the groups. We needed to split the variances among the group. So with the answer that we get, we divide it by the number of group. So in this case, our number of groups is 3. The number of group is 3. Okay. So now let's start with the calculation of the sum of squares with the individual values minus the mean of each group. That's the first method. Summation of individual values or summation of individual observation minus the mean of the group square. Summation of the individual observations minus the mean of the group square. Summation of the individual observations minus the mean of the group square. So here we are going to organize our calculation well so that we don't mix everything up. You can do the calculation for all of them and sum all of them together, or you can do for each group, then for the sum of squares for each group, you add each of the groups together. You can do it and add for group 1, group 2, then group 3. You do it and add the 3 groups together. Okay. So for this, we are going to organize it into a table. So we are first going to do the calculation for the deviation for each group. Then when we finish, we square for each of them. And we finish, we square for each of them. So we have, for the first group, we have 643 minus 666.7. So we do the deviation first. Then we have 655 minus 666.67. Then we have 702 minus 666.67. So we calculate it and put it under the squared column. We put it under the squared column. So we pick each one by one. Then we square each result that we get. We are going to square each result that we get. So for the first one, we have 643 minus 666.67. So we are going to write our answer down. We do the calculations and write our answer down. So I'm computing it using the calculator. So for each value, I'm going to write my answer down. So for 643 minus 666.67, I got negative 23.67. Then I square it. So I put it under the squared column. Most of the time, when you organize your work this way, when you are making a mistake along the way, you get to spot it out. There are different ways of killing the cat. You can also sum all together if only you can differentiate between them. But more often, it's advisable to organize your work under tables so that out of the table you can be able to find out the trend, know where you are going to. So we'll be down for the first observation, group 1, which was negative 23.67 square. Second observation for group 2, which is negative 11.67 square. Then third observation for group 1, 35.33 squared. So for the first observation for group 1, I had 560.27. I'm sure you had the same. Then for the next one, we have 136.19. So, Mr. Julius, with our first calculation, the first time we made, the calculations we made, they are correct. I think the recently that we made, I think we got carried away with our calculations, so we ended up rather making mistake with the more recent meeting. Okay, so we've done for first group. We are also doing for the second group. So with the second group, we have 469 minus 473.67 for the first observation. So we calculate it, we compute it, then we write our result down. Then for the second observation in our second group, we have 427 minus 473.67. Then for the third observation for our second group, we have 525 minus 473.67. So we compute it, then we write our results down. So we have the result for the first one, negative 4.67 square. We square it. Then for the second observation in the second group, we have negative 467. We have negative 46.67 square. Then for the third observation in the second group, we have 53.33 square. So we compute the square for each one, then we write our answer down. So for negative 4.67 square, our answer is 21.81. 21.81. Then for negative 46.67 square, our answer is 2,178.09. Then for 53.33 square, our answer is 2,844.09. So we've done for the first group, which is compact cars. Compact cars for the first group. We have our answers for the first group. Then we have the one for the second group, which is mid-size cars. The sum of squares within for the second group, which is mid-size cars. Then we are now going to look at the third group, which is full-size cars. We can see that one. Third group, which is full-size cars. So we are going to do the computation for that one too. So we are calculating for the full-size cars, and we've gotten the sum of squares within values for these full-size car range. So we add all of them. We add the compact car to the mid-size car, then to the full-size car. We add all the three groups together. So therefore, our sum of squares within the groups, value, when we compute it, our answer will be 10,463.33. 10,463.33. Or we can use the variance approach. We can also use the variance approach to calculate for our sum of squares within. With the variance approach, we have the sum of each variance for the group multiplied by the degrees of freedom. And remember that for each variance of the group, when we finish, our answer will be divided by the number of groups we have. Group 1, 2, 3. So we have the variances as we see there. 31, 49, and 41.69. 31.18, 49.17, and 41.68. So we are calculating for the sum of squares within using the variance formula. So with that one, we compute the variance for group 1, then we multiply it for the degrees of freedom within, which is 6. The degrees of freedom within, which is 6. So 31.18 times 6, 31.18 square times 6. Then we do for the second one, we do for the third one. So when we finish, remember that we have variance for 3 groups. So we are going to divide by the number of group, which is 3. If it's one group, it's just 1. So we divide by the number of group, which is 3. So we got 30,757.20. Then we divide by 3. When we divide by 3, our answer will be the same as the one we did early on with our individual observation minus the group mean. Though it will not be exactly the same, we end up getting 10,000 as well. So with that one, we also get 10,000 something. So that's what you see being done there. 30,757.33 or 20 divided by 3, and that one will give us 10,252.40. You might not get the exact value, but they are close. At least they are close. They are within close range, because we are dealing with means and variances. But at least they are within close range. So we have 10,000. And when you do the computation, either for the individual values or the variation, you are going to end up either rejecting H2 or H1. You're going to end up getting the same value in our subsequent section. So now we've gotten our sum of squares within, which is 10,463.33. 10,463.33. So we record it we record it in our table nicely. Now the next thing to do is to calculate our total sum of squares. We always know that the total is between plus within. Total is between plus within. So total sum of squares will be sum of squares between plus sum of squares within. Bear in mind, we also have a formula for the total sum of square. Which is summation of the number of observations for each group times the individual observation minus the grand mean. So you do it for each observation throughout. But with that one is long, so we can just pick the short method, which is sum of squares total equals to sum of squares between plus sum of squares within, because we already have the values for sum of squares between and the values for sum of squares between. So all that we do is to add it. So we add 86,052.83 plus 10,463.33. So we add the two values to give us the answer for the sum of squares total, which is 96,516.16. Then we come and record it nicely in our table. So that our work will be in order. Now we are done with sum of squares. We are moving on to mean of squares. With the mean of squares, is what is going to help us compute for the F statistics. So the mean of squares, we are going to divide our sum of squares values by our degrees of freedom. So mean of squares is always sum of squares divided by the degrees of freedom. Mean of squares is always sum of squares divided by the degrees of freedom. So mean of squares between will be divided by degrees of freedom between. The mean of squares within will be divided by degrees of freedom within. So that's sum of squares between divided by degrees of freedom between. Then we get our mean of squares between. Then our sum of squares within divided by the sum of squares degrees of freedom within. That will give us our mean of squares within. So when we finish, we will go ahead to calculate for the F statistics, which is mean of squares between divided by the mean of squares within. Mean of squares between divided by the mean of squares within. That one will give us the F statistics, or we say F calculated. When we finish getting our F statistics, which was 25.18, we go and record it in our table. Then now we come and work for our F ratio. Our F ratio is comparing our degrees of freedom between by our degree of freedom within. So that's where we are being led towards the table. So we record our F statistics. Then we record our F ratio, which is F ratio is degrees of freedom between is to degree of freedom within. Degrees of freedom between is to degrees of freedom within. So we have 2:6. So we move on to our table. Then with our table, we are going to look at our p-value, which is 0.05, since we are from the social sciences. So now we have our table here, and with our table we have our significance level, that's alpha level, at 0.05. So we take our degrees of freedom within and degrees of freedom between. So degrees of freedom between is 2, right? Degrees of freedom between is 2. Then we compare to the degrees of freedom, which is 6. Then we get 5.14. 5.14. So we come and record it. You remember to record it also in your table. Remember to record it in your table. So degrees of freedom between is 2. Degrees of freedom within, which is 2:6, will give us 5.14 from our table. Now we compare our F ratio to the F statistics. So F statistics will be compared using the greater than sign, greater than or less than sign. Our F statistics will be compared to the F critical. F statistics will be compared to the F critical. And when we do the comparison, we realize that our F statistics is greater than our F critical, 25.18 and 5.14. Which one is greater? Realize that 25.18 is greater than 5.14. So 21.18 is greater than 5.14. So now we've been able to compare our p-values, and we find out that 5.18 is greater than 5.14. So using the normal distribution, we know that in ANOVA, we deal with normal distributions. So in comparing it, we realize that our critical value, which is 5.14, that would be our liver, right? Our liver. So that one will compare to the F statistics, which is 25.14. And in comparison, we realize that it's out of the region. So it's at the rejection region. So here we reject HO. Then we move on to our final stage 7, which is interpreting our results. Now that we have been able to state the decision rule of rejecting HO, we conclude by interpreting our results, saying that since the F statistics is greater than the F critical, we reject HO, which is our null hypothesis. Therefore, there is a significant difference between the mean pressure of the cars. Since the F statistics is greater than the F critical, we reject HO, which is our null hypothesis. Therefore, there is a significant difference between the mean pressures of the car. ANOVA is this simple. So now let's go over. So in going over, looking at our table here, as we've recorded, we have our hypothesis first, then our degrees of freedom, then our sum of squares, then our mean of squares, then our F statistics, our p-value, then we interpret our results. So we state our hypothesis, whether it's significant or not significant, then we deal with our degrees of freedom, then we record them in our table, then we come and work for our sum of squares, then degrees of freedom. Our sum of squares between, sum of squares within. It can either be individual values or using the variance. Then we come and look at our mean of squares. We look at our mean of squares, that is sum of squares between divided by degrees of freedom between. We do for between, then we do for within. Do for between, then we do for within, right? So sum of squares within divided by degrees of freedom within will give us mean of squares within. So that's the mean of squares. Then the mean of squares will help us calculate for the F statistics. That's F statistics. F statistics, we have mean of squares divided by between. Then we come and compare our p-values, which is here we found that F statistics is greater than F critical. Then we interpret our results. Since F statistics is greater than F critical, therefore reject null hypothesis.